Okay, so maybe we can start. So today we will try to have a very nice lecture, I hope. I'm quite excited about this one, maybe my favorite. It's quite a geometric lecture. And we're going to try to describe today some local behavior of analytic functions, and talk about open mappings, maximum principles, and then a very nice topic, in my opinion, just the automorphisms of the unit disk, which will also lead to studying automorphisms of various other domains in the complex plane. So a very key proposition, which is what we ended with last time, and it's very important that you keep in mind what this one says in order to follow well the course today. So I do a recap of this proposition by writing it again on the board. So it says that if f is a holomorphic function at some point z0, and then we use this convention of denoting always the image of z0 by w0, and then suppose that f of z minus w0. So suppose that this equation holds here with multiplicity n. So it means that the equation f of z minus w0 has a 0 of order n. At z equals z0. So we suppose this. And then the proposition said that for any sufficiently small, and this is actually very important, so for any sufficiently small epsilon, you can pick a delta such that for any u in the disk of radius delta around w0, we have exactly n zeros of f of this u minus, f of z minus u. So we have n zeros of this in the disk of radius epsilon. Okay, so this is kind of a little bit messy, this proposition. So you just need to get your head around it. So what it says is that you have z0 here. So for every epsilon sufficiently small, so now we take it quite small, then you can find, so this is inside some domain omega where your function is analytic. Then you mapped this to f of omega. And you had w0 somewhere in here. And then we showed that for every epsilon, there exists some delta here, such that if, let's say, the equation f of z equals w0, let's say that this had two solutions, right? Then we are saying that the equation f of z equals u, so if we take some other point u in here, then the equation f of z equals u must have exactly the same number of solutions as the upper equation inside this disk. Okay, and we said that this was something that absolutely doesn't happen in real analysis, because you remember the example was, simplest example is x goes to x squared. Then you can see that x squared equals 0 has two solutions up to multiplicity, but x squared equals minus epsilon has no solutions at all, even though it can be arbitrarily close to 0. So this was a special property for holomorphic functions. And then we also said that if we decipher this proposition a little bit, then what does it say? So take a point w0 inside f of omega here. And then what it says is that if we take epsilon small enough, then we can find a neighborhood inside here such that every neighborhood, every point here has a pre-image there. So what it says is that, in particular, it says that for any epsilon small enough, there exists a delta such that this disk is inside of the image under our holomorphic map of this disk in here. But this disk for epsilon small enough here, this one is inside of omega because omega was open. So this would imply that, in particular, this image is inside f of omega. And so now if we see what this means, then we said that if we took an arbitrary point inside W0 inside f of omega, then we could find actually a delta, which is the radius of some disk. So we could find a disk, a neighborhood, an open neighborhood, which is inside f of omega. So in other words, this means that f of omega is open. So the corollary of this, which is a completely immediate corollary from this proposition, along the lines that I explained, is the open mapping theorem that I wrote down at the very end of last time. So this is one of the big theorems, right, in complex analysis and actually also in harmonic analysis and other fields. And this one then says that a non-constant, so of course the constant analytic functions are an exception. So this wouldn't work if you had a constant function. So a non-constant analytic function maps open sets onto open sets. So we say that it is an open mapping. Okay, and having an open mapping is very important because if you remember from topology, the definition, the topological definition of continuity, then actually F inverse being continuous is the same as saying that F is an open mapping. So we will use this soon. So any questions about this so far? Okay, good. So now let us distinguish between two cases when we study. So for local behavior, local behavior around Z0 in our domain. Okay, F goes from omega to C. Then we distinguish between two cases. We distinguish between the first case, which is that the derivative is non-zero. Let's start with that. And then the derivative is 0 is the second case. And these two cases will have very different behavior, actually. So it will turn out that in this case, when f prime of Z0 is not 0, then you have a local inverse, okay? And in the case f prime of Z0 is equal to 0, then you don't have a local inverse. On the other hand, what you have is an n-fold covering behavior locally that is modeled on this example, z goes to z to the n. Okay, so we will see first what we mean. So look at case A first. And now we're going to refer back to this proposition again, which is why I said it was important that you try to remember what it said. So first note, the following, that f prime of Z0 being non-zero. So what does this mean? Well, this means that you had f of Z0. So f of Z, it's holomorphic. So it has a local power series expansion in the following way. And f prime of z0 being non-zero, well, what does this mean? It means that A1 is non-zero, and it means that you have a 0 of order 1. Okay, so what I'm trying to say is that corresponds to n equals 1 in the proposition. So saying that f of z0 equals w0 has exactly one solution locally, so in this disk. Okay. So now that this one has exactly one solution locally, we get from the proposition, so this will imply here, that actually f of z is going to be bijective. So again, everything is local, so don't make this mistake. So restricted to a map from this, some small disk around z0 to some small disk around w0, and this epsilon and the delta are provided by the proposition. Okay? So why is this? So of course, bijective, what does it mean to be bijective? I mean, it means precisely that if I look at the equation, if I take a point, so if I look at the equation f of z equals a, where a is in this disk here, and z is in a disk around, small disk around z0, then the equation f of z equals a has exactly one solution, right? So it doesn't have 0 solutions, it doesn't have more than one. So it is bijective. Okay, so f of z is bijective, and this means that in particular we can define an inverse, which is always useful, but a local inverse. Note well, okay? So local, not global. So f inverse of z can be, f inverse, because it's going to be taking values in w. So f inverse can be defined locally here as a map from the disk, the small disk in the w plane, to the small disk in the epsilon plane. So we have, again, we have this in the z plane, have f mapping to this disk around here in the w plane, and we have an inverse going back. Okay? So we have this inverse, and right now let me then make a remark. So a mistake not to make here is that, so f is locally one-to-one mapping, one-to-one non-to, around z0 in omega is exactly equivalent. So just to recap, this is exactly equivalent to saying that f prime of z0 is not 0. So this one is a phrase definitely to remember. You have a local inverse if and only if you have a non-zero derivative in the point. But, and this is the warning sign, this does not imply that you are globally 1-1. Okay? And can someone think of an example of this? So a function which is locally 1-to-1, thus locally invertible, but not globally 1-to-1.
Z squared.
Z squared?
Or any power of Z.
Any power of Z. So this doesn't have an inverse globally? Because
No,
we
it's
have a
not
branch
one-to-one.
cut, is your argument then?
No, it has roots of unity. Sorry, Z squared. I meant to say Z to the n plus 1. Sorry.
Z to the n plus 1. Okay, so I mean the inverse to this would be the nth square root, right? Or the n plus 1 square root, which is, yeah. Okay, so this is fine. So I will anyway give another example, anyway, which I think is even more convincing, maybe. It's even easier. So my example would be this. Z goes to e to the z. And why do I say it's even more convincing? Well, I think it's even easier because it's periodic, right? So you don't have to even think about this one. So yes. But yeah, sure, absolutely. You're right.
Professor?
Yes.
Is the inverse holomorphic as well?
If the inverse is holomorphic as well? Yes.
Yeah.
Yes. So this is what we will discuss on exactly the next page. So on the next blackboard, I will show exactly that. So I will say that by the open mapping theorem, it has to be continuous, but we can actually show that it's even analytic. So it's a very good point. This is what we'll discuss now. So, so first step, so by the open mapping theorem, we know that F inverse is so F inverse is continuous. So F is open, so F inverse is continuous. So why is that? So it's because of the topological definition. So by topological definition. Continuity, which would be what? So in this case, it would be that if U so U in f of omega, so now I'm slightly confused, but help me out here. Which direction am I writing with this one open? In omega, was this what I wanted to say? Let's see. Well, okay, so I think I wrote it wrong, but maybe. But so being continuous, so a map is continuous, of course. If you take an open set in the image, then the pre-image is open. So you know this definition. Okay, I'm sure it's clear for you, even though I got temporarily confused. So in fact, so we can even show it is analytic, but F inverse is analytic. And analytic, of course, so again, it's analytic on this small disk where it is defined, right? So we're not talking about any global properties. By the way, I could make a remark that, in the first homework, I was asking you to give some inverse, I think, of some function which was not globally 1,1, and as was remarked. And of course, the intention was that it's, locally invertible, and then you could give the power series expansion of the local inverse. So what I intended was something like this, right? And actually, we'll see probably next time what exactly I had in mind with this exercise. Okay, but so now let's see why F inverse has to be even analytic on this. So why would that be? So it uses the continuity, by the way. So what do we need to show in order to see that F inverse is analytic? Well, we need to say something about the derivative of F inverse, right? Because the definition of being, analytic means holomorphic, and the definition of holomorphic is that you're complex differentiable. So don't worry, we're not going to write down any difference quotients. So it's just that, so since we had f prime of z0 was non-zero, and f inverse, so continuous, so defined and continuous in the neighborhood of this W0, which is f of z0. Okay, so we're working now in this neighborhood. So here f inverse is defined. This other disk. So it's continuous at this neighborhood, and this means that, and f prime of z0 is non-zero. And this implies that actually the inverse is complex differentiable. So this is some theorem that belongs really in the first 3-4 lectures of the course. Immediately when you define the differential, you have this thing in real analysis as well, that if you have the if you want to differentiate the inverse of a function, then as long as you have sufficient continuity and something is non-zero, then you have the following formula. So you'll understand as soon as I write it down. So f inverse prime of W would be what? Well, it's exactly as you learned, I'm sure, in your first year of something, that it's equal to this. And we can note that this is non-zero because f prime of z0 is non-zero. Okay. So we have this formula for the derivative, and this one is, under these conditions, we showed the continuity. We assumed that f prime of z0 is non-zero. So assuming all of this, we can see that in a small enough neighborhood, f inverse now is not only defined by the bijectivity, but it's actually even analytic, because we just provided this using this standard result from that belongs in the first lectures. We showed that we have this this derivative. Any questions about that so far? So I can summarize this, by the way, by saying that in the following way, by saying that if f prime of z0 is non-zero, so now we are summarizing this case A that I talked about. We had the case when f prime of z0 was non-zero. So then, one way that it's often written in the literature would be the following, that says that when f maps a neighborhood, very long word, so neighborhood of z0 conformally and topologically, so this is usually how we put it, conformally and topologically, I will explain what that means, onto a neighborhood. Neighborhood became NBH, okay? So long to write. So a neighborhood of f of z0. Now, by topologically, so by conformally, let's start with that. So by conformally, I mean that it maps it just holomorphically. Okay. And even with holomorphic inverse. And topologically, okay, So this is something, of course, sort of weaker. But it means that you continuous with continuous inverse. Okay, so I think the conclusion that you can keep in your head is that if f prime of z0 is non-zero, then you have a local inverse, and everything is very nice. You will map a small shape. So if you try to map, an elephant using a conformal map with non-zero derivative in the region where you drew the elephant, then this will be mapped conformally, which means that all the angles on this picture of your elephant in this example will be preserved. Doesn't mean it will look like an elephant after you apply the map, but it means that it will look like some kind of deformed elephant. Maybe it has been bent in some strange ways. But the angles are preserved locally. So if you remember this lecture we had on the conformal maps. Okay, and this thing to be analytic with an analytic inverse, this is actually, so we will remark on this later, but this is what's called being biholomorphic, which is a very important word to know if you want to do more of complex geometry or complex analysis later on in your lives. Okay, so the second part is, so what about the case where f prime of z0 is equal to 0? Okay, so the prime example again, so I know we said something about this last time, but I'm not so convinced that this iPad thing is working out very great. So let me do it now with a proper feeling on the blackboard. So the example would be z goes to zn at z0 equals 0. So of course this has a 0 of order n. And so has a 0 of order n at z0. This z0 equals 0. And if I look at the image now of a small disk, if I take some open disk here with epsilon between 0 and 1, then this one, and I look at f of this, so this is f of z. So then f of this would cover a neighborhood. I'll explain what I mean by this. But this is the key phrase. So it would cover a neighborhood, again of 0, but of radius epsilon to the n. Okay, so just some small detail. Of course, the radius gets smaller. If you take the boundary of this disk of radius epsilon, then the boundary will go n times around 0, but it will spiral in. It will lose some radius. So the covering phenomenon exactly n times happens only on this smaller disk. So epsilon n is smaller than epsilon, of course, since epsilon was less than 1. Okay, so it covers a neighborhood here exactly n times. So what do I mean by this mysterious covering notion? So I don't know if you did this in topology. If not, you will, I think, for sure do it in algebraic topology, which is something that comes soon in this ICTP program. And so the image here is, the picture would be something like, let me first take the example z goes to z squared. So what would that one do? It would map half of a disk into a disk. So z goes to z squared. So it would map half of a disk into a full disk. Right? So if you look at the image of this under z squared, then you will always double the arguments, and you will, in the end, cover cover everything. I mean, depending on if you include this white line or not. But you will cover everything if you include it. And then, so this is the idea anyway. And then if you have, if I need to take a second color, so what about the second half? Well, the second half, the same thing happens. It's also mapped to the whole disk. And so in some sense, you could think of this, I mean, what topologists or geometers like to think is that what we get is kind of a stack of two pancakes sitting over this one pancake. So this would be the twofold covering of the disk. Okay, so now this is the unit disk, right? So these are all the unit disks. You would get a twofold covering. So I'm explaining now the intuitive idea about what you would mean by this covers a neighborhood n times. So it means that you have exactly this behavior of z to the zn. And so in the same way, I mean, if you take z to z cubed, then just to understand what happens, well, then we can divide this into this Mercedes sign here. And we get that this first third is mapped to a disk. The second third is mapped to a disk. And the third is mapped to a disk. And you get this stack of three things that you can naturally then project down to a disk. So of course, if you had some element here, then you just remember where it came from. It came from here. Okay. And this is how it goes. Okay. So you have this, I mean, this is kind of the intuitive picture that you can have in mind when you think about this statement with coverings. Okay, and then, so the question is, what happens in general? So of course, I took this example, z goes to the zn, z to the power n, but this is not by far, the only example you can take. There are many, much more complicated examples, and now we want to show that they also have some similar behavior to this. So the way to do this is to show that assuming this condition that f prime of z0 is equal to 0, so we are around in the neighborhood of a point where the derivative vanishes, then actually the function is not very different in behavior from this example that we just saw, z to the zn. And how to see this? So if we have this f prime of z0 is equal to 0, so we have that f of z minus w0, so this equation f of z equals w0, in the example it would have been w0 equals 0, so the equation zn equals 0 would have n solutions. In this case, we would look at the equation f of z equals some w0, which is f of z0. And then we would say, okay, this has a number of solutions. So this has n roots. So of course, it always has some number of roots. So now this is n. And it's just a non-zero number. So then we can write according to our very standard trick. So we know that this has a 0. I mean, another way of saying this is it has a 0 of order n. So a function which has a 0 of order n, we know all too well by now. If you don't know this trick, then there is no way you can solve anything on the homeworks, I think, anymore. So for sure you do. So it's equal to this times g of z, I wanted to call it, times g of z, where g of z is an analytic function, so in a neighborhood, so of course in a small neighborhood of z0. And moreover, g prime of z0 is not 0. Okay, so now we have this. And we could now look at this part here, and we could say that, okay, we have something like z to the n here. We have some simple function here. It's essentially z, just up to a translation, but translations don't really change in any way this covering behavior. So it's z minus z0 to the n. And then we have this g of z. Okay, so we feel like we are getting slightly close. I mean, we can start seeing why this would have a similar behavior to this power function, z to the n. But it's not quite just a power. So what we would like to do is that we would like to write this as z minus z0 times h of z to the n. And the question is, are we allowed to do this or not?
In a small neighborhood, g of z will have an analytic nth root, and we are allowed to do this.
Exactly. So we actually saw this in a homework, right? So I think it was the last exercise. Actually, I wrote down here what it was. So it was exercise 7 on the third homework, I believe, where I asked you to define the logarithm of g of z. So because, of course, as you remember, the nth root is defined using the logarithms. So this is true where, and I mean, you're exactly right, but we can do this in a small neighborhood. Because so h of z, so it's taken to be an analytic single-valued branch of this function nth root of g of z, which of course is defined to be g of z to the 1 over n, which is by definition then e to the 1 over n log of g of z. Okay, and log of g of z can be defined here in a small neighborhood. Of z0. And this is by this exercise. So, okay, there was something to do there for sure. But since you have, I mean, since this is part of the exercise sheet that probably you have seen, I'm not sure if in the tutorial you did that by now, but I think maybe you did. So, I mean, even if you didn't, you will. So I will allow myself the luxury of not repeating that argument here. Okay, so the claim is anyway that you can find under these conditions, you should check, remember, make sure that you remember that you can actually take such an nth square root. And now then you write this off, here you have exactly the function w goes to wn, but then composed with whatever is in here, where h is analytic with non-zero derivative, I guess, and then you have this part here. So let's try to So this f of z minus w0, but I put the w0 on the other side. So it's equal to w0 plus z minus z0 times h of z to the n. And this is then a composition. So this is a trick that we used at some point before in the course. You remember that we wanted to see that something was conformal, and then we showed that it was a composition of translation, rotation, and something else. You know, if you go back and remember in your lecture notes. So in this case, it's a composition, well, of a translation, first of all, with w0. You have a translation. Z goes to z plus w0. Then you have z goes to z to the n, this kind of behavior inside here. And you have z goes to z minus z0 h of z. Okay, so the most complicated part. But here, so we want to know if this one is nice or if this one contributes maybe in some way that would be similar to z to the n. So, but it will turn out that this one will fall in the first category, the one where the derivative is locally non-zero, which means that we have what I wrote on the rightmost board here earlier, that it maps a small neighborhood conformally and topologically onto a small neighborhood in the image. So this third point will behave nicely, and it will be, so to see this, you just differentiate. And you differentiate it in, and evaluate the differential in z equals z0. So this is equal to, so we need to evaluate h of z plus z minus z0, h prime of z in z equals z0. So this is equal to h of z. So h of z, it was then this nth square root here. So h of z0, sorry, even. And h of z0, you can check that this is non-zero. So this last part means that it maps this small enough disk, so epsilon is small enough, conformally and topologically onto this small disk of radius delta here. And, see step A for this. So by step A. So we have a translation, which is, of course, just, a very trivial thing. So it doesn't, it's conformal, of course, and all these things. And then you have this z to the zn, which we studied, and we saw that, okay, we know that z to the zn, it winds around n times. It sends all the points on this journey, n times around the origin. And this will lead to an n-fold covering. And then you have this one, which is, again, then nice and locally one-to-one. So what you will get is that is the following. So the conclusion is that the image of a small neighborhood around Z0, the image under F, covers a neighborhood of W0, so equals f of Z0, exactly n times, okay? And a way of thinking, again, about this covering n times, if you're still uncomfortable about this, I will propose the alternative way of thinking about it, which is that If you have an n-fold covering above your small neighborhood, it means that each point there has n pre-images, right? So just like the solution, just like the equation z to the n equals your favorite number, will have exactly n solutions up to multiplicity, then this is what it will mean also in general, that each neighborhood, every point in every neighborhood has exactly n pre-images to the equation, f of z equals this point. Okay, I hope it's somewhat clear what I mean by this. Otherwise, please ask. And the final remark, so I wrote already earlier that there is a local inverse exactly if the derivative is not 0 in the point. So now we are in this case that f prime of z0 equals 0. So there is no, so I just want to underline again that f has no local inverse. So the inverse would be defined around w0 equals f of z0 if it existed, but now it doesn't exist because the derivative is 0. And again, the reason for this existence exactly if f prime of z0 was non-zero was because of this proposition I wrote down on the first board of the lecture. So, okay, so we have this. And I just wanted to point out that just like all of these local behaviors of analytic functions, essentially, it's not true anymore for real variables. So we like to make these comparisons. So why is it not true? Well, for very many reasons. When I say in real variables, I mean in the usual setting. It's a shorthand for the usual setting in real analysis, meaning calculus, not the course that you're having in parallel here with Manuel. So an example would be f of x equals x cubed, which looks like this. I hope you can see. If you cannot see, please tell me, and I'll change the board. You know what it looks like, so it's not super important, but so this one is locally 1, 1. So of course, its derivative vanishes in 0. On the other hand, it is actually locally 1 to 1, around 0. Even though its derivative vanishes there. And it has an inverse, which is continuous but not differentiable at x equals 0. Okay, seem to be able to see. Good. So this is a special property of, again, all of these local properties are very strong. You should really meditate on them and realize that things that you study outside of complex analysis usually absolutely don't satisfy these strong conditions. Okay, and now as a fundamental, very important application, extremely important application actually. I think my entire field of research would just cease to exist if this result wasn't true in complex analysis. So, maybe slight exaggeration, but not entirely. And this important result is what's called the maximum principle. And I think it's also so important because it's used in so many different contexts in mathematics. So even if you don't want to do complex analysis, you want to do, many other things, harmonic analysis, you want to study PDEs, just anything basically that has any analysis element in it, even if it's a lot of geometry or something, uses this maximum principle at some point, I would say. So maximum principle for analytic functions. because there are other maximum principles that are, the same thing, but in other settings. For example, harmonic functions. Okay, and this is an application of the open mapping theorem. And again, the open mapping theorem was an application of this proposition that we saw, and the proposition was saying it was providing us with these neighborhoods that we've been working with throughout this lecture. Okay, so the maximum principle says the following. So suppose that F is analytic. So on a domain U of C, so this is open. This is very important, right? So we have some open domain, some open connected set in the complex plane. And then the statement is that if the absolute value of f of z attains a maximum, just like in the sense of, in calculus, you learned that if you have a compact, on each compact set, a continuous function attains or achieves the maximum of this function. Now we are looking at actually a real valued function here, the absolute value of f of z. If this one attains a maximum on U, so even a local maximum, then the conclusion, as so deceivingly often in complex analysis, the conclusion is that then f has to be constant. So what this means is that if you take a non-constant holomorphic function, then it cannot attain its maximum on an open set, in an open set, but rather it would attain its maximum on the boundary of this set. So if you have some open set, and you look at the absolute value of f of z, then its maximum has to be, so it cannot be on the interior, but it has to be somewhere on the boundary. And I will ask you a very stupid question, so please forgive me for that, I guess. But just the remark is that why am I looking at the maximum of absolute value of f of z and not of f of z? Just to connect to the first lecture. So I'm claiming it would be very stupid, of course, to ask about the maximum of f of z, but what is the reason?
There is no ordering on the complex numbers.
Yeah, exactly. Thank you for the answer and for hopefully forgiving me for asking you such a trivial question, but I still wanted to point this out. So it's easy to sometimes be too quick and forget this kind of things. There's no ordering on complex numbers, so that's why we're looking at the maximum of the absolute value of f of z. Very good, thank you. So alternatively, let me write this also in a positive form. So this one says that, okay, if you have an analytic function, you have a maximum in the interior, then you have to be constant. But it's often nice also to have the alternative form of this, the so-called positive form. So if f is non-constant and analytic, and k is some compact set in U. So this is compact. I hope you can see what I'm writing, but it's not k. It's some compact. Then f attains, so this is what I said in words, its maximum, absolute value of f attains its maximum on the boundary of the compact set K. Okay. So this is what I said. So now, let's see, how can we prove such a theorem? So the proof is actually very easy again. Once you have the open mapping theorem, it's very easy. So what we do is we can suppose, for contradiction, that W0, this f of z0 in our notation, is a maximum of absolute value of f of z in the open set U. So I'm using now the formulation in white, right? So the positive formulation. So if you suppose that you have a maximum, so you have this open set, U open, you have a maximum here in W0, which is f of z0. And then, of course, we want to say that this is a contradiction unless the function is constant. So suppose this and assume that f is non-constant. So then we can apply the open mapping theorem. To see that this set f of u is open. So, so this is, of course, so u is open, but this was f of u that I drew, because w equals f of z0. So I'm looking at the image of u, and I took some w0 in there. But so this is an open set by the open mapping theorem. And if it's an open set, well, what does that mean? It means that it contains a disk, right? So f of u is open by the open mapping theorem, not by hypothesis. So we can take such a disk. There exists a delta such that the disk W0 delta is contained in f of u. So this is what I drew in the picture. Take a small disk. And now the very nice idea of this proof is that, okay, this is an open set in the complex plane. Okay, f of u is in C. I hope you can still see what I'm drawing. Maybe not. Where's the camera? Okay. So f of u is in C. And the origin is somewhere. So the origin could be inside, but the origin could also be outside somewhere. So let's say that this is the origin, okay? So when I'm looking at the function, the absolute value of W0, then it means just the distance to the origin, okay? But since, this is a disk, then it's immediately completely obvious that there has to be a W in here for which the absolute value of W, the distance to the origin, is larger than the absolute value of W0. So what I'm claiming is that there exists a W in this disk, in this disk, W0 delta, such that absolute value of W is strictly greater than absolute value of W0, but this W is inside of f of u. So it means that W is equal to f of z for some z in u, and this was equal to f of z0. Okay, but then this means that actually you found, so you supposed that W0 equals f of z0, so z0 attained the maximum, or the maximum was attained for z0, but now you found some other z where the absolute value of f of z was even larger. Than the absolute value of f of z0. And this is then, of course, a contradiction. That means that if you have a non-constant function, it's impossible to have absolute value of your holomorphic function having a maximum in some open set. On the other hand, if you took the closure of this open set, then it would be compact, being closed and bounded in C. And then this absolute value of f of z is the absolute value of a continuous function. So it's a continuous real-valued function. It has to attain a maximum on the compact set, the closure of this disk. The closure of this set, U. And hence, since it cannot be in the interior, by what we just said, the maximum has to be on the boundary. Okay. Any questions about this? Again, by the way, this one fails in real variables. So you can think of why. Okay, so let me just write here, if so fails. Real variables, the maximum principle, that is, because we can take, for example, x goes to 1 minus x squared. And if we look at this on the interval 1 to minus 1, we get this. So the maximum is in x equals 0. Which is an interior point of the interval, the open interval minus 1 to 1, where the function is defined. So you see, we don't have a maximum principle in real variables. So again, something special, something strong. This results. Okay, still no questions on the maximum principle? Not, then we will go to the topic analytic maps on the unit disk. Okay, and the unit disk will always be D here. So unit disk is D, which is the open unit disk. This is the picture we shall have in mind. And now we want to see, okay, we want to study analytic maps on the unit disk. So by this, I will study f that goes from D to D, okay? This is what I mean by on the unit disk. If I just had some analytic map, from D to whatever other region, then, it would not be the same thing. Now I'm studying from the disk to the disk. And then it turns out we have some quite strong restrictions on what can then happen. And I should also mention already now as a motivation that this disk is a prototype for a more general problem where I can ask, okay, f from omega to omega, how does this one behave? Well, in many cases, you could find an explicit, maybe a Möbius transformation or an explicit biholomorphic map, so an explicit holomorphic bijection with holomorphic inverse between D and omega, and then by understanding all the analytic maps from D to D, you could then use this identification, because being biholomorphic is the notion of isomorphism in the category of complex manifolds, if you want, or of these complex of these open subsets of a complex plane. So then you can use this to understanding the analytic maps on the unit disk, you can understand the mappings, analytic maps from omega to omega.
Professor, does omega need to be bounded?
So omega here would be a domain, so it would be an open bounded set, I would say. in practice, I mean, no, actually, it doesn't have to be bounded. Yeah, it doesn't have to be bounded. No. An interesting remark, I mean, when you ask this, by the way, is that what is the difference between a bounded and an unbounded set in complex analysis? So sometimes there is a difference, of course. But if you look at the unit disk on the Riemann sphere, so the unit disk on the Riemann sphere, it was equal to the southern hemisphere, everything below the equator, by the stereographic projection identification. On the other hand, if we look at the unbounded set, which is the complement of this set, the complement of the disk, then it will be everything in the north hemisphere, maybe excluding the North Pole, right? So in some sense, the unit disk viewed on the Riemann sphere doesn't look more bounded or unbounded than the complement of a unit disk.
No, actually, when I asked this question, I was thinking about, can we put omega to be the C hat?
Can we put omega to be the C hat? So if we put it to be the C hat, then we have a problem.
It's not open. Yeah, it's compact.
Yeah, then it's compact. So then we have a problem that all the holomorphic functions are constant. But we can put it to be, for example, H to be the upper half plane. So for example, so this is an example later. So H, upper half plane. So this is an example of some unbounded thing. So what I mean is this. Imaginary part, strictly positive. So if we look at maps from H to H, then we can understand perfectly these maps by understanding the maps from D to D. And we do this by mapping the disk to the upper half plane using a Möbius transform. And then we know that Möbius transforms, they have a nice inverse, and this will preserve the properties in a sufficient sense to be able to describe also the maps on the upper half plane. Okay, but we will see all of this now. So the very key result. So this is really, again, this is a very, very useful result here. So this one you should definitely remember. Don't go to the exam without remembering this result. And it says the following. So if F is analytic on D, so what I mean is that I'm looking at F from D to D. And I also assume that F of 0 is equal to 0. Okay? So my map goes from D to D, and it fixes 0. This is the condition to apply this Schwarz lemma. So if you have to be a bit careful, remembering that F of 0 must be 0 for this to apply. Then we have the following 3 conclusions that we can say about this map. The first thing we can say is that the absolute value, sorry, that is very stupid. So the absolute value of F of Z is less than or equal to the absolute value of Z. And of course, all these statements are true for all Z in D. We are now always in the disk. So this is always true. The second thing is that the absolute value of the derivative in 0 is always less than 1. So you have some control over how fast the absolute value of this function, analytic function from a disk to itself, can vary in 0 or close to 0. And then the third point, which is by far the most useful, is the following. Let's see, can you see down here? So it will require a few lines. So yeah, actually, let me erase and write it over here instead. It's better. So the third point of the Schwarz lemma is that so there are 2 conditions that you can use, but it's not 2 conditions, but it's just a choice of whichever of these you prefer. So if the absolute value, if there is some point, Z0 in the disk, such that the absolute value of f of z0 is exactly equal to the absolute value of z0. So this means that you have equality in 1, okay? This is the first thing. So if you have equality in the first condition, or if you have equality actually in the second condition, so if you have equality in either of the first two conditions, then you can say, you can draw some very strong conclusions about the function f, which is not quite that the function f has to be the identity, but it's of the form lambda times z. So it just lambda times the identity, so to speak. So lambda times z for some lambda in C with absolute value of lambda equal to 1. Okay, so remember this. So we have this conclusion here with absolute value of lambda equal to 1. And what does this mean? Well, it means that when you multiplying by a complex number with absolute value equal to 1 means that it's actually a rotation, right? So it's a rotation. This is my remark, my interpretation of this thing. So this is a very nice, very useful result. Let's look at the proof. Okay, so for the proof, we consider, so there are some proofs, of course, in this course that start by considering some strange functions that immediately you don't know why you should be considering them. Okay, this one is not so strange, but still, you'll have to follow the argument for a little bit to see. So we write down this function. So when this function, is it analytic on the unit disk or not? Is the first question. Do you have an answer to this? So f is analytic, which means that this part here, where z is not 0, then still f of z divided by z is analytic. And then putting f prime of 0, so remembering that f of 0 equals 0, putting this will actually yield the, it will complete this function into something which is analytic also at 0. It has a removable singularity. So g of z is analytic. It has a removable singularity, if you wish. This f of z over z has a removable singularity at z equals 0. So f of z over z. So now the idea is to apply the maximum principle. So to see how this powerful tool can be used. So apply the maximum principle to this function g of z. So let's see what we get. So consider the closed disk defined by absolute value of z less than or equal to r, where r is less than 1. Then we know that the maximum of the absolute value of g occurs on the boundary. And the boundary of this disk then being absolute value of z equals to r. Okay. So we have this, and this disk sits inside of the unit disk, which is the domain we're looking at. Then the maximum has to occur on the boundary. And what does this imply? Well, this implies that absolute value of g of z is then less than or equal to whatever the value of g of z would be on this boundary. Okay, so we just said the maximum of the function g of z, I mean absolute value of g, occurs on this circle here, on the boundary circle. And the boundary circle there, the function, first of all, we're not in 0, so the function is equal to f of z over z. The absolute value of z is equal to r, and the absolute value of f of z is less than or equal to 1, because we have said that f maps the unit disk to the unit disk, which means by definition that absolute value of f of z is less than 1. So f of z is less than 1, and absolute value of z is equal to r, not less than, but it's equal to r, we get this. Since absolute value of f of z is less than or equal to 1, and absolute value of z is equal to r here. So we get this. So letting r go to 1, what do we get? We get that absolute value of f of z is less than or equal to z. Okay? Because absolute value of g of z, so because g of z is equal to f of z over z. Okay, when z is non-zero. So we get this, and we also get, so we get the first 2 points, basically. That this is less than or equal to 1. Because absolute value, so saying that absolute value of f prime of 0 is less than or equal to 1 came from saying that absolute value of g of 0 is less than or equal to 1. Because absolute value of g of z was less than or equal to 1 over r for all z in the disk, precisely because the maximum principle said that the maximum had to be attained on the boundary, where the maximum value on the boundary was 1 over r. Hence, the maximum value on the whole disk was also 1 over r. Okay, and now we have to finally prove the last part. So this proved 1 and 2, that we have these estimates. It's a consequence of a maximum principle. Now for the last part, so finally, so if we have equality in 1 or 2, let's say, so if absolute value of g of z is equal to 1, so this means, yeah, so is equal to 1 for some z0 in the disk. This is what it means. So if we have some point where the absolute value is equal to 1, then by the maximum principle, yeah, so what would the maximum principle say? So the maximum principle says that, okay, we have a maximum which is in the interior, I mean, it's in some open set, the open unit disk we are studying now. So it's not on the boundary of this set or something. So by the maximum principle, it says that there is no choice for this function but to be constant. The function has to be constant, so g of z is equal to lambda for some lambda in C. And moreover, well, absolute value of g of z0 was equal to 1, so absolute value of g of z0 must then be equal to absolute value of lambda, so absolute value of lambda must be 1. So now we proved this part. And the other condition that f prime of z0, absolute value equal to 1, also means precisely this. So doing this, we are done. And we showed that f of z is equal to lambda z, which represents a rotation, if we have equality in Schwarz's lemma. Okay, so let's look at some application of this. And the application will be to the question of sort of uniqueness in some suitable sense of functions from the disk, or actually of conformal maps in general. So application is to this question, so to what extent are conformal but holomorphic maps unique? Okay, so we're not going to give a super general answer of this, but let me formulate the more precise version of the question I want to treat. So suppose that f and g, so we have now two functions that go from omega, which is some open subset of C, but it's not necessarily the disk. So suppose that we have two holomorphic functions. Holomorphic, and suppose that they are surjective. Okay. Surjective onto the disk. And suppose also that they map 0 to 0, both of these functions. Okay, so we put some conditions, right? So what we will show is that if we put these conditions, so we assume that both of them map 0 to 0, which is not as strong a condition as it might sound. It just means that we map the same point to the same point, essentially. Because if it's not 0, then you can arrange so that it becomes 0 and so on. So if we map 0 to 0, and we are surjective onto the unit disk, so this definitely happens in quite a lot of cases. So if we have two such functions, then we are related in a strong way. So let's first sort of draw it, what's happening. So we have this, let's draw omega here in the middle, and let's draw d on each side. So let's say that this is g and this is f. And then we have the map here would then be f composed with g inverse. And then so we study this map, f composed with g inverse. And if we would succeed, for example, to say that f composed with g inverse is equal to identity, say, then of course it means f is exactly equal to g. And now we will use Schwarz's lemma to say that it's something close to the identity. Of course, it's going to be lambda z. Okay, so we're going to be related by up to a constant with absolute value 1. So what we want to say is that by Schwarz's lemma, we have the absolute value of this is less than or equal to, so the point here, of course, is that why am I looking at f composed with g inverse? The point is that it goes from the unit disk to the unit disk. And it sends 0 to 0. So Schwarz's lemma applies. So this is why I'm looking at this function. Okay, so on the other hand, if we now look at this this point here, f composed with g inverse of w, and we say that we call this by some name, by calling it Z, then we have the following. So let's just see what things are here, just to make sure that we're writing the correct thing. So this thing here is what? It's equal to, so Z was equal to F composed with G inverse of W. So this one is the inverse of this one. So this one equals W. With F, so this one is exactly what's here. And this thing here, well, this is, again, then equal to W. So what I did was I just rewrote this inequality in a different way to get this. But this then, here is equal to, so of course, so I rewrote just this inequality, but the point now is that this one is the inverse of this one, so this is also just equal to absolute value of Z. Okay, so so it means that, okay, so what do we want to do here? Back of all of this. So if you use Schwarz's lemma again, then according to my notes here, we're supposed to get this. Let's see if we can. So then we get this. Okay, yeah. So we could apply Schwarz's lemma to this function. Schwarz's lemma says this, and by just rewriting the first application of Schwarz's lemma, we got this thing, which said that, so this is the same thing as what we have here, right? So here we said, so here we got less than or equal to absolute value of Z, and from this one up here, we got larger than or equal to absolute value of Z. So this means, putting these two together, we get equality here. Okay, so we just messed around for a little bit to find that actually we have equality here. And now we are happy because this means we have equality in Schwarz's lemma. So equality in Schwarz's lemma means that.
Rotation.
Yes, a question?
Rotation. This is just rotation.
Yeah, this is just notation, exactly. Yeah. We are messing around with notation just to understand this. But of course, I mean, we're using Schwarz's lemma and messing around with notation.
Professor, I have a question.
Yes.
Just confusion. Maybe I'm just confused. Why is this F composed with the inverse well defined? We're just assuming that it's surjective, right?
Why is F composed with G inverse well defined? So F composed with G inverse here.
I can't see it.
Ah, sorry. Yeah, I'm not sure where the cameras are. There are several, yeah. Okay. So, yeah. Would you just allow me to finish the sentence over there and then we go and think about this? But anyway, I mean, yeah, my answer will be that if it's not and if there's a mistake, then put the hypothesis so that it is. But we'll check this in a minute. So I just wanted to finish Schweiz's lemma. So G composed with F inverse of Z must then be equal to lambda of Z for some lambda with absolute value 1. And this means then that I can put the F on the other side, if you want. So hence, this means that G of Z is equal to lambda times F of Z for this lambda is equal to 1, which then implies that F, the slogan would be that F is unique up to this rotation, multiplication by lambda. By Schweiz's lemma. Okay, so unique up to some rotation. So now I can stop here, and now we can try to just think before we leave and have lunch. Since we close nowadays at 1, I cannot be as sloppy with going over time anymore. So now, why is this well defined? Okay, so we just have to look at this. Of course, it's not a difficult problem. So. We have a map. You're allowed to help me if you want. So D maps into some subset maybe of omega where it's surjective. So how do we have G inverse? This is your question. If it's not injective, we do not have necessarily G inverse without restricting then to a smaller set. Yeah, okay, I don't know right now, but okay, if you want, let us say that it's bijective then, if you wish, and then we are safe. And then let's think about this surjective part.
Thank you.
I'm a bit tired, yeah. I'm sure it's easy enough to figure out. Yes. Okay, so now we went through all of this, and so what's left? So the really important topic that's left, in my opinion, is with automorphisms of a unit disk. So this is what I will start with next time, and then I will also talk about this solution to the bonus problem in the first homework. So I will say what I meant by that and present something called Lagrange inversion theorem or Lagrange inversion formula. And then when I taught this course last year, I tried to give some kind of outro, so the opposite of an introduction. So to connect again with the first half hour of this course where I was talking about Riemann hypothesis and these things. So I tried to say something about the Riemann hypothesis. Already last year, I think I went over time 20 minutes just to do this. Now we are already a little bit behind, so we're probably looking at no lunch at all on Tuesday if I try to do this. So I might skip it, or I might just give a much shortened version of this. Although, of course, I understand that you might be interested in just seeing something about the Riemann hypothesis connected to complex analysis. So do you have any wish about this? Last part, how much you want to see this Riemann hypothesis at the end?
I want to see it completely.
You want to see it completely, yes. So good. So we'll give an extra half an hour lecture to finish this. But Yeah, okay, so I will see what I can do. So the alternative would be to cut down on this Lagrange inversion, possibly, a little bit. Because the automorphisms, they are, I mean, this is a super nice topic, probably my favorite. So this one we'll definitely do properly. This,
maybe we consider starting earlier.
Starting earlier, yeah, it is possible for me. I mean, for me, I'm not doing anything the half hour before. The room might be free, yeah? Yeah, so why not? I might email you then about starting like 20 minutes to 11 or something like that. And then we could try to do everything. Would that be okay, or for you?
For me, it's okay.
Yeah, I think it is a good option.
Yeah, everybody agrees? Well,
Yeah, it's okay.
okay.
Yes, yes, yes.
Good. Okay, so then I will consider doing that then. Yeah. Okay, so any other, and I'll do it in Budinich because it's much nicer to do it than this Blackboard. Okay, any other questions, or we go have lunch? Okay, so thanks for today, and I'll see you on, yeah, so unusual time next time. It's on Tuesday, because Patricia put it on Tuesday. So let's see you on Tuesday. And have a good week.